Okay, so this is a replacement class for the interrupted class of last time, where our plan was to cover that that the gauge structure of quantum mechanics, to present quantum mechanics as a gauge theory, and then to understand that why you need electromagnetic field. This is the part we were able to do last time. And then I wanted to tell you a bit about how, in general, gauge theories work in quantum mechanics, but that I will tell a bit late. But before that, I want to talk about this thing called Arnold-Bohm effect. So, so the sequence is suggest a book more descriptive. Yeah, this is actually a difficult point. I think you will get all the point from Sakurai and Griffiths, but not in the way I am telling you. It's not a because usually the gauge theory description doesn't appear in the context of quantum mechanics. I'm not so sure. It's described in this way, the way I am telling you. So yeah, it is different. I'm telling you it is different, but the appreciation of the gauge theory and the gauge structure is so for the purpose of syllabus, it is enough to know what is there in Sakurai and Griffiths. But how I am telling you is a bit different from both of the books. MIT coursework 30. Is it Zuivek's course? Yeah, maybe you can look it up there. Yeah, but I think I'm telling you things a bit differently from any book, and you can expect that. I mean, that is why if I'm telling you things which is there in book, then why come to class? So you can expect always something a little different. So I would suggest that look up at least Griffiths and Sakurai, and maybe this MIT coursework. I have not seen that course, but I think since it is taught by Zuivek, I think then it must have some aspects of that, some non-trivial aspect definitely. Okay, so let's talk about gauge theory in general. So we understood this point that local gauge symmetry of Schrodinger equation demands presence of EM fields, and we understood this point. So this point need to be boxed. It's such a cool point. We understood this point by asking that I have a local gauge transformation e to the power I alpha xt. So at this point, I am going to make a bit of connection with other theories in physics, because this local gauge point appears again and again in physics. It's not like that. It's everywhere. I mean, gravity. You can, if you take a course on general relativity, you will see that gravity emerges as a okay, let me tell you, I will tell you a little more descriptively later that if you demand that your theory, your dynamics, Newtonian dynamics or whatever, like your relativity, special form of relativity, is invariant with respect to local local transformation local translation and rotational transformations of fields, then you get for that gauge invariance you have to bring in gravity. So it is like but it's a purely classical demand. It's not there is no quantum mechanics in that, and you will eventually realize that you can visualize gravity as a gauge field without the need of quantum mechanics. But to visualize electromagnetic and other things, you need the quantum mechanics, and that is where this problem of quantizing gravity appears so difficult. Anyway, let's not get into the complexity, because to fully appreciate that point, you need the structure of field theory. But here we are doing everything from a quantum mechanics perspective. And you can appreciate the point, at least what is going on, and how the game. So so let's just focus on the basic stuff. Then I will do a little bit of how does gauge theories work in general. So and it's a very common sense, it's a very logical thing. You don't need to bring in a lot of non-trivial techniques for that. So we demanded this transformation. We demanded that my Schrodinger equation minus grad square minus h cut square by 2m grad square plus vx psi equal to E psi. Actually, I want the full dynamical equation, not the static. To be invariant, and we see that it is invariant only if there is a xt and phi xt that transforms as the way a gauge field transforms as em vector and scalar potential, but the arbitrary function is the same alpha xt. This is what we understood. Okay. Now the other point which I made on the first day was that these two equations, which is something I asked you to check, and I believe you did that. It's a very easy exercise. That if I give you these two forms of Schrodinger equation, so both of them has this psi del t 1/2m a prime. Sorry, this is psi. Now, if these two guys, this phi a and phi prime a prime are connected by a gauge transformation lambda, which is lambda is with a you have to add grad lambda, and with phi you have to add del phi del lambda del t in order to get phi prime and a prime respectively. Then these two psi, so this, let me call it a psi prime. Then these two psi's are connected by, is the other flip side of the previous statement, e to the power I q lambda xt h bar psi xt. Now this is a very useful tool to figure out if I give you a particular field and what is with the form in the other field. And it can be so that you can even work it out for various gauge equivalent configurations. So you will see in a moment an application of that when I'll talk about Arnold-Bohm. So up to this point, is everything clear? So what I plan today, I'll tell you some simple example based on these ideas, and then I'll go, and that is basically something I expect you to know as a part of the syllabus, and it's there in textbooks. Then I'll go a little more beyond that, which is not, I will not say, don't take it as a syllabus exam thing, but it's for to learn about how these gauge theories work. So is everything clear up to this point?
Sir, you said that the Schrodinger equation is invariant, and that will imply that a dash and a and phi transform in the fashion
No,
like
Schrodinger equation
EM.
in the absence of a and phi is not invariant.
Okay.
So it
But
is, this is like you have to make it gauge invariant, you have to bring in those two that way. So for example, you can ask, what if I solve a particle in a 3D box problem? Let me not go to 1D and 2D because you have to be careful about the form of Maxwell equation. So if I take the particle in a box problem, 3D box, and multiply every wave function with an arbitrary e to the power I alpha xt, right? Then I fit it, I plug it back in Schrodinger equation, satisfy Schrodinger equation. No, right? The derivatives will be there will be time derivative, they will mess up, right? So
right.
this is the meaning of that statement. Then you need an electric field and magnetic field to counter those terms that arises for that arbitrary factor.
So that means that the Hamiltonian has to include a and
Yes. Now you might be wondering, then how come Schrodinger equation is if it is not gauge invariant, is everything okay about it, right? You might be
Right.
wondering that, but that this A field, these fields itself can be zero, right? You don't need, so these terms can be zero, but the fact that there must be electromagnetism somewhere in the world, okay, such that
Okay.
you can
Uh-huh.
add those functions, the field
Okay.
can be
Okay.
zero, right?
Right.
Or the
In that.
field can be non-zero in a way that the measurable electric and magnetic fields are zero. All those things
Hmm.
can happen, but you cannot live in a world where there is no field which transforms that way.
Okay.
If you
So
want
in a
a,
local region, it can be zero, but it
yes,
has to. Okay. Okay. Got it.
yes. So that why there is finally justice prevails in the world. Okay. Okay. Okay.
But apart from A and phi, there can be also other functions which can help in making Schrodinger equation gauge invariant, right?
Yeah, but you need to keep it this way, right? What do you mean by
But
other function? That doesn't transform in that way. Is that what
so
you mean?
like there can be some functions now apart from A and phi which I can be put in
Yeah,
some
there can be
combination to make.
potential V. There can
So
be
yeah,
there can be
exactly.
some other potential, but that doesn't matter, right?
So
That is
why?
just a multiplication.
But
So in this
we have
equation,
introduced we are
let's say you add a potential Vx, right? Which is because of some, let's say you put this problem in a harmonic oscillator, right? It can be totally there, but that doesn't matter. It's a negative factor.
but we are introducing electromagnetic fields by assuming that starting from these two potentials, right? So if I start from some other potentials, can it be
Yes.
some introducing some other fields which are not even
Uh,
EM fields, something like that?
Sorry, say that again.
So like we are saying that local gauge symmetry of Schrodinger equation demands EM fields, right? And we
Hmm.
are starting from assuming there are two functions A and phi.
Hmm.
But instead, if I start from some other function x and y, which decide to become gauge invariant. So will this x and y also give rise to some emerge some fields
Yeah, so
which are not EM fields
anything,
but some other
so the
fields?
point is anything, any set of fields that is consistent with this local U1 gauge invariance. Local U1 means something you are multiplying it by a phase factor and U1. Anything that is invariant to that have this form. Now, if you demand this to be something else, then it can be something else. And in fact, that happens. Of course, in a single component function, you cannot do anything about it. That's the only thing you can do. But if you have a multi-component wave function, like the way things we learned in last semester, spin and etc., then this instead of U1, it can be something else, an SU2 or something. Then you get some other kind of fields, right? Is that question is, or I am answering something else and you are asking something else? You don't
Yeah,
sound
I'm
very
saying it,
happy
but
or
I was
convinced.
asking like if there is some physical significance of other fields also.
No,
Are there
of
some other
course there
fields?
is, but so for example, I mean to say,
The doubt was like, is can
so
you
you
predict
can add an
properties of that?
arbitrary potential which is not electromagnetic, right? Like you are doing these problems in particle in a box harmonic oscillator, right? Are you trying to say that kind of examples?
Yes,
So just plug them in. They will not
somewhat yes,
create
yes.
any connection with the local U1 gauge. They will not pose any problem. But you need this phi. That other field, which doesn't pose any problem, it is there in the original Schrodinger equation. Let's say you have this V, right, and there is no electromagnetic field anywhere. Then of course this will have some term which the extra terms that will pop out from the local gauge transformation will not be, this field will not be able to counter that. To counter that, you need a field that transforms in the way electromagnetic gauge field transform. Right?
Mm-hmm.
Make sense or?
Yes, 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 absolutely.
Yeah, I hope it's not a proof by intimidation. So you should be very careful about when I, just because I'm assertively saying something, that doesn't mean you have to accept it. You should keep arguing. That is
Yeah, it's open
ideal
to it's
scenario, but
question.
classes are finite. That's the problem. Anyway, that's why I tried this. That classes should be all debate, but it somehow didn't go well. Anyways, so is this point clear? So shall we do something else? I will come to return to this gauge point, but let me first do a little bit of a simple example of the kind which we already discussed earlier. That and this is actually the more famous example of Arnold-Bohm effect. where the wave function sees a potential, couples with a potential, and not the field itself. Let's discuss an example of that, and because that's, but it's not a new thing which you have not learned yet. It's easy but legendary example, and then we come back to this gauge point and go a little deeper into that from a unusual example. Okay, so shall we go to that example? Okay, so let's talk about a simple problem of, so this problem is again, it's the best place to read it is Griffith. So the problem is following. So let's say I have a solenoid. Okay, so this is effect. This is a famous experiment which shows this point of how you can manipulate the phase of a wave function, even in a way that even though it is not seeing a magnetic field or a particular field. So, and the example was discussed actually in two different contexts, one in around 1949 by Ehrenberg and Seidel, but the Arnav Bohm first made it like make a prediction and did the experiments, and it took a long time. No, sorry, Arnav Bohm predicted the theory in 1959, and the experiment happened right in next year in 1960, and the electrical experiment happened much later, I think in 90s, because the electrical experiment is much more difficult. The electrical Arnav Bohm effect. So let's discuss the point. So the idea is very simple. Let's say you have an infinite solenoid, and you have learned in a electrodynamics course for this kind of problem we have done, I think, many times, that if I have a infinitely long solenoid, it will it will generate, which means you wrap a wire and the current passes in a particular direction, it will generate a magnetic field which entirely passes through the center of the solenoid, and the B is totally zero outside. So let's say this is the current, no, current is entering like this and exiting like this, and this will be the magnetic field, and the B is non-zero only in the inside the solenoid. Now if I put a charge particle here at some radius B trajectory, it will not see this magnetic field because there is no magnetic field in that. So let's try to do the quantum mechanics of this problem. And the idea is simple. You have done this kind of assignment problem, that the vector potential is like this. You can write down the vector potential to be, so the idea is, let's write it down more clearly, that B outside 0 and inside, and everywhere it must satisfy the two constraints. One is that B is curl A. So you have to find the A that satisfies that. So A must satisfy these two, that A dot dr is by M closed. And you have done in electrodynamics that this is curl A ds, that is B dot ds, and since there is a B that is piercing this surface, so then the B is non-zero, and that means you get a by M by 2r phi cap in cylindrical coordinate, of course, because of the cylinder is, it's a cylindrical symmetry is there. This is across the contour, and it's some path of integral. Let's say it can be any arbitrary shape around the solenoid, and this is the total magnetic flux. Total. So the main, even though B is confined in the solenoid, A is non-zero outside. Okay. Now we want to do quantum mechanics of this problem. Now, before we do quantum mechanics, let's just recap once what happens when you put a particle on a ring. Okay. So you did this problem earlier in the previous semester. So we learned that if I have a particle on a ring with nothing inside, nothing in the middle, the equation is just this. And this I can rewrite in the language of spherical or cylindrical coordinate, L theta 2, and this is basically this grad square psi, and it must satisfy the constant. So if I call this angle theta, it must satisfy the constant that psi theta mod square d theta is 1, and psi theta, because it's on a circle, so at theta plus 2 pi are basically same point, so it must satisfy these two constants. So we learned that what these two constants give us, it gives us this two wave function, two eigenfunctions, which is e to the power plus minus ir by h 2m e theta. And if I do the eigenvalues, if I calculate the eigenvalues, is so this is like a left moving mode and light. So I can rewrite these alternatively in a simpler way using the I. Okay. Because of the square root condition. So this is something we learned. So there are, you can visualize it that one is a wave function moving in that direction, another is a wave function moving in that direction, and they have this possible. So now I want to ask the same question. I have this guy, and I have I insert a solenoid in the middle. Right? Now that means your naive classical thinking will tell you, of course, now you know quantum mechanics, you know something is going to be different. You are already like shock immune because of the quantum mechanics course. But your naive classical thinking will tell you what? That if this problem is no different from this problem, because the particle anyway doesn't see any field, any electric field or magnetic field. It just sees a vector potential, but that is not real. The force is exerted only by the field, right? Not the potential. So your naive expectation is these two problems are identical. But now let's try to work out a little bit of algebra to see what does quantum mechanics tells you. Okay. So let's do just it's. I think this exercise is trivial for most of you now, and it's all worked out nicely in Griffiths. So this is my Hamiltonian now. Let's just follow the prescription of writing the Hamiltonian with a magnetic field, where A is phi by 2 pi r phi cap, when r is greater than A, where A is this radius. Okay, it is there. It's outside, all outside. So, and the phi is not pi a squared. Okay, magnetic flux to solenoid. So this quantity, if I expand it, it is 1 by 2m minus h cut square grad square plus q square a square plus 2i h cut q a dot grad. Now notice there is also another thing you can introduce, that is grad dot a, but let's work in the Coulomb gauge where grad dot a is 0. Now the phi doesn't enter in this game, the phi is 0 anyways. There is no potential here. So now if I write the Schrodinger equation, it will become, clearly the Schrodinger equation will change. So now we want to see how the observables are changing. Okay, I am using phi for this one, and here I have used theta. Just be careful. So this is phi, but that doesn't change anything. It's just a choice. Okay. Now I can massage this equation and make it sleek. So it becomes d2 psi d phi 2 2I beta 2 d psi d phi plus, where beta is 2 phi by 2 pi h bar. So is minus beta square. And now I plug in an answered solution, a trial solution, just the way we did earlier. And that will, once we plug it in, I get a quadratic equation, because a second order differential equation. I get lambda beta square plus epsilon as beta plus minus v by h bar 2me. And I impose the condition that, of course, psi at phi is same as psi as phi plus 2 pi m, because it's on a ring at the end of the day. So that will give me e to the power this and e to the power this v by h bar, and this will, how we'll get the quantization condition, will be giving me this. Okay. Oh, my battery is low. Okay, it should not be a problem because the tablet. What? Let's see. Should I move somewhere else close to the
Sir,
plug?
can you please scroll up
Yeah.
while you are adjusting your phone? Thank you.
Here.
Sorry?
Here.
Yeah, a little bit upwards. Yeah, thank you. Yeah, that's fine.
Yeah. Yeah. I will send you this thing in PDF. So don't worry about copying it, and it's all there in Griffiths anyways, the algebra.
Okay.
Yeah. So now I have this form. So that means En is h cut square by 2mv square n minus, so this put the constant n minus q phi by 2 pi h bar. So now you can see there is a clearly difference in the observable, because in this case we saw this. It means it doesn't matter whether the that this object have actually a degeneracy, whether the particle is traveling in the same direction as the current or in the opposite direction. Okay, but this one lifts that degeneracy. It clearly has an observable term q phi, which is not something you expect in classical dynamics, because there is no field in the place where the particle is. So even field B at particle location is 0, the particle knows, not the particle, the wave function of the particle knows about the B and couples with the potential. So this is the point I wanted to make. And then an interesting consequence of this point is to how it leads to.
Sir, will you repeat the steps again?
Okay, this is an easy step. I mean, just all I did, I took this guy, I squared it. Okay. If I square it, I will get two terms. One is del acting on A and A acting on A dot del and del dot A, right? I remove the del dot A because it is I use Coulomb gauge. So I have this Hamiltonian is this form. One is grad square, one is A square, another is A dot del. Okay. Now this is the same algebra we discussed earlier. Now I am at this point I am writing this in a cylindrical coordinate. Grad square becomes this phi square. This I have written the a, I have squared the a, and this a becomes this phi. There is only one coordinate phi, right? It's confined on this ring. Now I am massaging this equation a bit to make it clean looking. So what I am doing, I am just taking this coefficient and passing it everything on the right hand side. So when I do that, I end up with the equation which I only have d2 psi d plus 2i beta. The beta means this 2m goes here and gives you this beta, and similarly this guy goes here and gives you this factor of epsilon. And once we get that, so okay, there is a first derivative term, and then there is a constant term, not constant term, there is a term that is dependent on E, and this is the E minus this quantity, so that is why I have this form. Now I want to solve equation with the trial solution, and the standard trial form is this. So I plug that in, I get this quadratic form, and then I impose the constant that since it is on a ring, and if it returns to the phi after 2 pi, every 2 pi rotation, if it returns, then it must satisfy
Okay.
the constant. That gives me a quantization. And when from the quantization, I work out the energy eigenvalues, and the energy eigenvalues have a extra phi dependence in it. And that tells me even though the particle cannot see the field directly, it knows about the existence of the field somewhere else, and it directly shows up in the energy eigenvalues.
Well, it can experience the field.
It can experience
Though.
but so the point is there is no B where the particle is, but the curl A is also 0, but the A is non-zero. That point is okay. So now let's try to take it towards something you can measure. Okay. So how to do that? Let's say the how to write the wave function. So the wave function will be grad minus qa square. Where the particle is, the wave function will be this plus v psi I is bar del psi del t. Now v you can drop that v also because there is no electric potential or any other potential I'm talking about right now. So then the solution of this equation will be psi times e to the power ig psi prime. So this is what we learned today and earlier also, that if there are two set of, okay, now I need to do something about plugging in the laptop. Where can I plug it? There is no plug. Okay, give me just 2 minutes. I'll just take my charger and plug this. Okay, I'm back. So okay, so now I want to see what happens to, so we just saw that what happens to the eigenvalues when I turn on such a field. So now let's see what happens to the eigenfunction. Okay? So to work that out, I simply know that if I have a field and if I turn on a field, I can work out the influence of that on the eigenfunction just by, if I know the solution without any a field, if that solution is psi prime, and then I turn on a field that is given by some pure gauge, so then pure gauge means it just have a goes to a prime plus some 1 by q grad alpha. So then I can rewrite this in the form of that. So here I'm calling it just this whole thing, just something we wrote earlier today. So let me rewrite that. So this is e to the power iq alpha by h. So this whole thing, e to the power iq alpha by h, I'm rewriting it as ig. So then this g is nothing but q by h bar o to r a r prime. A dot r prime, some arbitrarily chosen point, and r is some other point. So is the point till which you are taking that integral. So but note that this in order to use this must be true. You can write this in the region where grad a is 0, so where curl a is 0. So now if that happens, so then you can write this grad psi as e to the power ig I grad g I grad g over root. So I am just 2 lines of algebra is there which I am skipping, and I am just coming to the final conclusion. Just take up this algebra, and you will land on this solution. So what's the point of this exercise? The point of this exercise is, if I have this equation and I want to know what is the solution of this equation, and I know the solution of this equation, then I can use this solution, which is psi prime without any gauge field. Use this solution, multiply it by some e to the power ig, where ig is this something that involves that gauge field. Then I'll get the solution of this equation. So this is the point of this equation exercise. So this is, if I know solution of 3, I can write the solution of 1. This is without any gauge field, any a, with a, by psi prime e to the power ig is psi, where ig is this particular factor, as in equation 2. So now how it will work out here? So let's say I want to know the solution of the problem when I know the solution of the problem without the magnetic field, without the flux. So that means I have to just calculate the g, which is q by h bar a dot dr. Now a is, and if I plug that in, it becomes q phi 2 pi h bar phi cap r phi cap d phi, that is plus minus 2 phi by 2 h bar. So if I multiply this by your psi as e to the power I q phi by 2 h bar with psi prime, which is the original solution, without the gauge field, then I'll get the full solution. That is the meaning of this. And this is exactly what it follows from what we discussed earlier today and in the past day. That if I have two set of fields which are connected by some gauge transformation, I can go from one to another by doing this operation. Okay, now let's see what is the consequence of this in some observables. Okay. So this is basically now the main point of AV proposal, Anugraham proposal. So what did they say? They said, let's do a double slit experiment of this form. There is some source here, and as you know, in double slit experiment, the electron goes from these two paths and does some interference here. Okay. Now the proposal is, let's put a solenoid here. Okay. Now if solenoid here, then I can take this enclosed path, and we learned here that there is a degeneration in these two paths which goes along some direction, and the path which goes opposite to that direction. So there is a degeneracy between these two, but if you turn on this magnetic field of the flux, then that degeneracy is broken. So the experimental setup is like following. So if I look at it like that, if I look at it from this view, so this is the two double slit. From here I'm sending the electron, and the solenoid is kept like that. Okay. Solenoid is kept like that around some cylinder, and here is the slit. So the electron is going this path, and it is encountering this solenoid in the middle. So we know that what will be the interference pattern. It will be some rho e to the power ik. If I take the cylindrical coordinate, you get to multiply by this factor. So this is the path 1, rho 1. So let me call this sigma 1 and sigma 2, these two slits. So e to the power ik rho 2 by rho 2. And what is this ik rho 1? It is nothing but, so this is without any magnetic field. Without any magnetic field when the solenoid is switched off. Okay. So now with magnetic field, what happens then? So I will get a ik rho 1 by root rho 1 e to the power ie by h bar a dot dl s sigma 1 sigma. So this is my S, this is sigma 1, and this screen is sigma. So in this picture, this is the S, this is sigma 1, this is sigma 2, and this is the capital sigma. So it will pick up a phase just like this from O to R. So origin is S and it is ending at sigma. And similarly, the next one will get that. The other path will get to the power ik rho 2 by rho 2 IE by h bar a dot dl s sigma 2 sigma. Okay. Now I can take one of these terms common. I can take this whole term, this first term common, and the second term will be 1 plus e to the power I capital delta, where delta is k rho 1 minus k rho 2 e by h bar S sigma 1 sigma a dot dl minus S sigma 2 sigma a dot dl. Now what is this thing? If I take this in this direction, and if I take this in the other direction, the S sigma 1 sigma, I take it in the arrow direction, and S sigma 1 sigma 2, that path I take in the opposite direction. It's basically taking this whole circular trajectory. So it will become k rho 1 minus k rho 2 plus e by h bar a dot dl. Okay. So now I know how to, I just worked it out earlier. So my grad is nothing but the usual interference pattern plus E grad phi by h bar. So what was that A dot dl? We worked it out earlier. Yeah, q phi by 2h bar. So this is sorry, I am using E here because this experiment was used for electron. So E phi by 2h bar. I think there is some pi factor also. Let me check if that is true. No. Okay. So q phi by 2h bar, and the phi is proportional to the magnetic field. So that means this proposal is saying tune the magnetic field in the middle of the, if I take an infinitesimally thin solenoid, which the electrons is somewhere is right behind the slit, then the electron's path will be modified by that, electron's phase will be modified by that. That means my interference condition will be modified by that. So if I tune the magnetic field, I can create or destroy the interference pattern at a particular location, and I can shift the interference pattern. So this was the proposal of Arnov and Bohm, and which was verified in the next year by an experiment. So this whole statement that a wave function couples with the potential, this is the another one of the quantum mechanical experiment which you cannot even think of physics. Okay, does this example make sense entirely?
Yes, sir.
Okay. This experiment is very difficult to do with electrical field, but the point is this, just this. It happened much later. Okay, everybody is clear about this?
Sir, how would you physically explain the thing is going on? Like
Yes.
why or how the particle is feeling the magnetic field inside?
Yeah, the point is that is correct. So if physically it is very there is no satisfactory explanation if you try to think in terms of the gauge field. So one way you can think is the following. So you have to give away the classical notion that the force is the physical object and potential is the unphysical object which you use to generate the force. So that means you have to say that the wave function, which is itself not a measurable. So there are two ways to think about it. One way is more straightforward and more linked to what we have just done. So one way is I will say that the potential. So I have to throw away my classical thinking that that field and force are the real thing and potentials are fictitious object to generate that. And then I have to accept the fact that a electric field, a magnetic field is the part which is physical is the vector potential that generates the magnetic field, and then wave function couples with that field, and all the observable effects you get are because of that coupling. So this is one way of thinking it, and this is how I formulated the problem. But if I want to go, I want to keep my my notion that a physical object or the wave function can only see the magnetic field, then probably I can think it in this way. But it won't be entirely satisfactory. I can think it is this way, since until measured, the wave function is everywhere. The wave function is everywhere. It can be anywhere, right? The particle can be anywhere. So even though you are thinking that okay, the particle is not going there, but you don't know that until measured. The particle might be seeing the magnetic field. Okay, but if you think in that way, then you will be a little more satisfied because you will get to keep your classical idea that the particle interacts with the field. But that is not apparent from the formulation because the field directly doesn't enter into the formulation. Okay, and I will tell you there are more counter examples. I will just tell you in 2 minutes, just as a story. I will not formulate the problem, where you can engineer the field and engineer the field by creating a fake effect of the field by engineering the phase of the wave function. So if I leave aside that point, does it sound at least a little more, what will I say, little more satisfactory, where I tell you that if you want to keep the notion that a particle interacts with the field, then you can keep it by saying, until measured the wave function is everywhere, then it might be seen in the field. But it is not consistent with how we formulated it. Okay? Make sense?
For the first thing you said, that I mean potentials are much more. I mean fields are fictitious in this case, and
Yes.
potentials are kind of real.
Fields are not even needed in this case, because there is no notion of force. If you notice in your quantum mechanics problems, there is no notion of force, right?
Yeah.
You can calculate a force by saying expectation value of derivative of potential is force, but you don't need a notion of force to think about. And
But
you,
to
if you think, yeah,
generate the potential, I ultimately need to create some field, like by creating the current, then the field will come.
yeah,
And
yeah. So let's
otherwise,
think about
if there is no field at all, then there will not be any A there. I
that.
need
Is
some
that is
current
not
or
that is
B.
exactly the point we are saying here. We can have a even if there is no field, right? Well, you can say there is no field nowhere, right? Even then there can be a, as long as it is consistent with the gauge, right?
Then where is it coming from? I mean, if there is no field, then where is it the A's are coming from?
Yeah, so this is the question, that what is more fundamental, that like God created human or human created God? So it's like that. So so if you like to think in this way, that let me put it in this way, as a how you graduate to this idea. So initially we thought with mechanics that there cannot be a force without physical contact, right? And then gravity came. Then you say, okay, there is a field when there can be a force without physical contact. And then you came across electric field and magnetic field, where you can say things can interact with each other without a physical contact. And how you measure the magnetic field is by putting a compass, by measuring the force on the compass. So even the field itself is not something that you experience. What you experience is the Lorentz force that it inserts on the compass, which you measure, and that tells you what is the deflection of the needle, which you use to draw those field lines, right? So the fact that we say that the field is the real thing is just a bias of our mind, right? There is no reason a priori to say that. So what is more fundamental, field or potential? This is the question that comes here. You see what I'm
Sir,
saying?
so in the classical limit, why does the field seem so much more important? Why
No,
aren't
it's
the
just
effects
the
of
way you
potential?
formulated the theory. It is just the way you formulated the theory. If you start with Hamiltonian, then the field, then what is more important? The potential, right?
Hmm. But if you start
But
with
if you start
Coulomb,
with the Lorentz force and Newton's equation, the force seems more fundamental. But you neither experience the field, right? What you experience is actually the force, right?
yeah.
So it is a bias that to say that what is more fundamental.
So
And
we can
quantum
say
mechanics
that.
brings you to that bias. Yeah.
So we
Yeah.
can say that there is potentials everywhere, and
Hmm.
there are some cases like if I turn on a current or something like that, that
Hmm.
place starts to create the field because of that potential or something.
Yeah, it tries to distort the potential field.
Okay, okay,
Yeah. So
okay.
this is the viewpoint that quantum mechanics is forcing you to adopt. Okay.
Yes,
Now
okay.
let's dig a little deeper into that. So I told you about a fun example. So I want you to, some of you, to dig up in this topic, and there are very nice term paper topics you can think. Some folks did it last time, so go a little deeper into that. So there is something called synthetic gauge field. It is a type of experiment in condensed matter, because right now we have realized that you can what happens when there is a gauge field, right? When there is a magnetic field. When there is a magnetic field, the particle experiences a change in the phase, right? Now, what if you can engineer that phase by some other way without the magnetic field? So this thing is called synthetic gauge field, where you are creating a fake experience of magnetic field without any actual magnetic field. So they can be done in various different ways in cold atom experiments. And there is another way is by engineering the strain. So strain engineered gauge. So look up this topic, strain engineered gauge field. Look up this topic and you can find something more interesting. Now there is one more point I have missed deliberately, which I will come back a little later, is that this kind of phase, these Arnold-Bohm phases, they are a type of Berry phase. They are called a Berry phase. If you go to Sakurai, you will see a discussion on that. But I will come back to this point later when we will do perturbation theory. That's where naturally the Berry phase will come from there. And then we'll come back to this to connect these two things. Okay? They are something very interesting and fundamental in physics, and they can be also measured. So actually you will see something. So let me make a broad statement, and the statement is gauge invariant quantities are all the observable quantities are usually gauge invariant, are gauge invariant. And you will see this Berry phase, you will see this when you learn this Berry phase, you will see this phase, this flux, this phase, because of this interference and whatever, they are also some gauge invariant quantities, and that therefore they must be measurable in various other contexts. And one classic example of that, one of you can again take it up as a term paper, is that if you measure current in a conductor, there are certain scenarios where you can see that the current is the Berry phase directly influences that current. It's like a current voltage measurement. And there are examples where you can show that this can be quantized, which means the current can be quantized, and that is where some topological effect enters into quantum mechanics. So if you don't understand this, it is fine. I am not even trying to explain. I am just telling you those topics exist and giving you as a suggestion to pick up for term paper. Now, another interesting topic you can look up is the topic of magnetic monopole. Now, we know there is no magnetic monopole in nature, but you can formulate electrodynamics by assuming that there is some magnetic monopole just for the sake of symmetry. So even though the electrodynamics, as we know, there is no magnetic monopole, there are examples in many body physics like spin ice, where you can have an emergent effective electrodynamic theory with a magnetic monopole. This is also something else you can pick up, and we will return to this discussion later also. That's why I'm not going into that, because you need some perturbation theory, etc. background to set up this problem. And but it is a nice term paper topic. And another topic is Dirac quantization. So you can look up this. So the Dirac quantization is another, it comes from this quantum mechanics and electrodynamic theory. You will see that if there is a magnetic monopole, it satisfies this kind of a quantization. E is the electric charge, G is the magnetic charge. Now, we know that there exists electric charge, and electric charge is quantized. All electric charge's nature is a multiple of electrons electric charge, right? Electric charge is quantized. But there is no theoretical explanation for that. To explain it theoretically, you need a magnetic monopole, but we know there is no magnetic monopole. So this is an outstanding puzzle, and you can look up in this topic as well. So with this, just a little bit of background, a little bit of peripheral topics, let me come back to this question of gauge field and try to give you a little better understanding of gauge field from a slightly different perspective. Okay. So I will give you the references for this because this is a little offbeat topic. And the reference is, there is a physicist called Eric Weinstein, who uses these gauge theory principles in economic models. And there is another YouTube lecture and an article by Juan Maldacena, who is one of the founding fathers of ADS-CFT correspondence, and he is extending this gauge theory in many other contexts. So he gives a very nice elementary talk where he explains what these gauge theories are, etc. So the main point is that gauge symmetries are not really symmetries of nature, but rather it's a symmetry of the description. Okay. And to explain that, he gives an example to an economic model. So the idea is following. Let me see my notes. How do I write it properly? So for example, if you look at in our daily life example, daily life experience, so we use many fictitious quantities, right? Like the concept of money, concept of nation, they are all fictitious quantity. The physical reality should not depend on that. Like how you define money, it's a artificial gauge, artificial measure of your wealth, right? So it is and it is of course local. How India defines their money and their value, assign the value, is different from how USA does that. And it's not only local, it's dynamical also. It depends on various other factors. It's a very complex problem, of course. I'm not going to enter in that problem. But the example he gives is that let's say there is a lattice, and in that lattice, every point, every vertex is a country. Okay? And he sets up a game where, so let's say this country is USA, whose currency is dollar, as he gives this example. This country is Argentina, whose currency is peso. This is Europe, which is euro, etc. So, and the rule of the game is you can go from one of these country to another. So these lattices are basically a bridge that connects these two countries. And in the bridge, there is a bank which exchanges money. So let's say a traveler can go from one country to another country through the bridge. And when they go from the through the bank, it exchanges all their money, what they have, and then reaches this country with that with their currency. And the bank can have an arbitrary exchange rate which they decide locally. It doesn't care about what others do. The bank that, for example, give an exchange between euro and dollar, they don't care about. This is a very idealized game, of course. It's not true in real world. Everything is connected to everything. That's why economics is a hard subject. And it also depends on many other soft factors which you cannot buy, panic and etc. So then the rule of the game is the person can go wherever it want, whichever country. Only rule is it can only go through these bridges, and whenever it goes from one country to another country, it must convert all this money. And the question is, can the person earn money in this way just by doing this? Okay. So let's consider a scenario. And now there another incident can happen, that each country can arbitrarily impose a local gauge transformation to their money. And he gives an example actually. So it can happen sometimes. For example, if some country, let's say some inflation happens and they accumulate a lot of zero in their currency. So he gives an example, let's say the cost of a banana becomes 5,000 peso in Argentina. Actually, this thing happened in Argentina many times. They did this kind of gauge transformation. So 5,000 peso it becomes. So let's say it says, no, I will call it 5 peso instead of calling it 5. So he gives some other name. I forgot what name he gave. Instead of calling 5,000 peso, I give it a different name, some 5 something else. Like I have 5,000. Let's say I have everything is transformed in terms of this 1,000 factor. Now this transformation doesn't change anything physical, which means a person who is richer will remain richer. Rich, poor, that hierarchy will not change. It's a global scale. It's a local transformation for that country, but within that country system, nothing changes. But as they redefine their currency by removing these zeros, So he gives actually the example of Argentina, because he says when he grew up in Argentina in 1916 and versus now, the difference between the currency at that time and now is 10 to the power 13 factor, because of this inflations happened and they readjusted the scale and all those things. Countries do that. Luckily our economy is stable right now. That's why we didn't experience this. But places like Turkey and all are going through that kind of phase now. So now that doesn't change any interrelation within that country. It's a local scale transformation. But it changes, of course, the exchange, because now if 5,000 peso is 5 peso, then it changes the exchange between this country and another country. Now the question is, does this kind of local change can decide the factor whether that person, if the person takes a loop, whether that person will earn money or lose money or something. So he gives a scenario where the person earns money. So the scenario is following. So let's say this guy goes from, in a triangle, one is euro, another is peso, another is dollar. So that means, so let's say the exchange is arbitrary and 1 euro is $1.5 and 1 euro is 10 peso and $1 is 10 peso. So clearly if the person goes like this, comes back, goes from Europe to USA to Argentina and comes back, that person can increase their wealth by, increase their money by 50%. Okay, so this circuit will give you 50% gain. Now, will that gain depend on the factor whether a country can do a local transformation for their internal currency, and that accordingly adjust the global scales. That turns out that it doesn't, right? So this is the meaning of a gauge transformation. So a local transformation that doesn't change the principle.
Sir, can you please repeat the last thing you said before,
Yeah,
like
so
saying
the
that there will
question,
be 50% gain?
yes. So the question is it possible? So you know this circuit means you gain 50. So if you start with $1, you go here, you get $1.5. From here you get this guy is breaking the symmetry, right? This is 10 peso, 10 peso is 1 euro. It's nothing happens here. But in this line, since 1 euro becomes 1.5, that means here you have $1.5. That means here you have 15 peso, and this 15 peso means 1.5 euro. So when you return, you have 5 euro, right? 5 euro extra. So not 5 euro, sorry, 0.5 euro extra. So you earned for 50% of your what you had, right? You understand this point?
Yeah.
Yeah. So the question is, if these countries apply some local transformation to their currency, okay, then, and if I adjust the exchange rate, this field by that, according to that transformation, it should not change the fact what amount of money the person is gaining by this circuit, if any at all. If it is not gaining, not gaining. If it is gaining something, whatever it is gaining, that factor will not change, right? You see what I'm
This
saying?
point is not clear. That last statement.
Yeah. So if a country changes their scale, right? Let's say I say whatever is 10 peso, I call it 100 peso or 1 peso. And I change this transformation accordingly, right? You see what I'm saying? That should not
Yeah,
alter
yeah.
the whether this person or what happens to this person's wealth when it goes through this complete closed circuit. Do you follow this point?
Yes.
Yeah. So this is the meaning of a gauge transformation. This is a colloquial example of a gauge transformation. That if your local sticks are changing, and you're adjusting that stick transformation, that should not change some of the observables. It's not applicable in all the cases and all the problem. But this problem is set up in this way. Of course, we set up the problem, we define the problem in a way such that this happens, right? So does it make sense? Does the example make sense now?
Yes.
Okay. Nilanjana, do you follow this?
No, the last statement is not very much clear yet. Like I understand the 50% gain, but then you said about something like ultimately the I mean the observables is not changing. So
Yeah,
I
so
cannot.
if I call 10 peso as 1 peso,
Mhm.
okay, and if I change this transformation as $1 to 1 peso, right, that should not change anything.
Yeah.
It's a local change, it's a local transformation, and that is not changing my the observable effect, which is wealth of the person when
50%
it
gain.
returns. Okay,
Yeah.
so that is why I'm calling it an example of a gauge transformation of the similar sort we discussed earlier. Now this kind of example happens everywhere. For example, this problem I discussed previous day, that if I have a space-time fabric like this, and I apply a local gauge transformation at each point, right? So what is this e to the power I alpha xt? It's a unit circle, right? It's not in physical space, of course. It's in Hilbert space, but it's since it's a function of x and t, there is a unit circle at every point. And what I'm adjusting here, that where this point should be, if I have a arbitrary local transformation. So how I measure the wave function at each point is arbitrary up to this factor because of this multiplicative thing. Makes sense? This is the meaning of this gauge transformation, right? Do you follow that this is the meaning of this gauge transformation of e to the pi alpha xt?
Yes. A
Okay.
little bit.
Now I demand my theory should not care about this transformation. If I demand that, then I'm just interpreting what is the meaning of this. If I demand that, then Schrodinger equation fails to satisfy that demand. But if I add these extra fields a and phi, then this extra field will adjust, which transforms in that way. Then it will adjust the arbitrariness that comes because of this local transformation, such that my theory is gauge invariant. Then all my dynamical observables and every variable is gauge invariant, right? So this is the meaning of a gauge transformation or a gauge symmetry, right? So some theory doesn't have gauge symmetry, some theory has. Similarly, you can define a quantity in this example, which is not invariant with respect to a gauge.
Sir,
It
so
is,
here A and phi are analogous to the exchange rate.
yes, correct, correct. Now this example can get more complicated. It can get more complicated in the sense that I can have a SU2 multi-component field and etc. So this is, I'm just giving you a a physical intuition of gauge theory. So gauge theories can come in even much more simpler form. So let's give an even more simple gauge theory. So let's say I have some, you are going to a space battle, okay? So you have some spaceships. Now you want to know what is the position of this spaceship. How will you do that? You will do that by measuring, let's say these are spaceships from Earth. You will do that by measuring the coordinate, their coordinate, right? So let's say the physical quantity that matters is xi minus xj. So you have some radar system to measure distance. But there is a gauge transformation here. Can you see what is the gauge transformation? So this is the physical distance. Can you see what's the gauge transformation? It's trivial, right? Every xi, I can add an arbitrary lambda. Then it doesn't matter. Physically speaking, it doesn't matter what is the position of your first spaceship, because all you can measure is their relative distance. You can send some signal, it comes back to you, measure the distance. You have nothing else against to compare it with, right? Do you follow this example?
Yes, sir.
Okay, now let's say there is another alien fleet, okay? Now they have another set which has a defined gauge. Okay. Now if you want to measure what is the distance between your fleet and the alien fleet, then these two gauges must have to match. Right? So this is another interesting example that you require gauge fixing when you need a coupling between two different gauge theories. Okay? You will appreciate this point much later when you learn the coupling between electromagnetic field and matter field. Right now, you saw this kind of a Hamiltonian, right? You saw the Hamiltonian is P minus QA, right? QA acting on psi, this kind of a momentum, this psi. So this is a coupling already, but I have not discussed it in this language because phi is a wave function, A is a field. But when you learn QFT, you will see that phi is also a field. Okay? A is also a field, phi is also a field. So these coupling terms are usually requires gauge fixing and it breaks the gauge. So this is a simple example that the position of the first fleet with respect to which you are measuring the position of the other fleets, that quantity is gauge invariant. But and only quantity, the measurable, is the relative distance between the fleet. Now, if you bring in another system, which is another alien spaceship, and they also measure their own fleet with their own gauge. But when you couple them, then if you want this total object to be gauge invariant, then you have to fix these two gauges. Okay, so this is a kind of example where these you see some non-trivial effect of two systems or two kind of gauge theories when they interact with each other. And how do you deal with that? That's a little non-trivial. So I will not talk about that here, but I want you to just appreciate this point, that how non-trivial are these gauge theories and how cool are their effects. But if you have understood this point, that is enough for now. Is it making sense or you are getting confused? If you have not understood this example, I'm sure you understood this example, but if you have not understood why did I bring out this example, it is all right. But did you understand up to this point, this local gauge invariance and electrodynamics? Any comment?
So the previous example about the currencies and all, the exchange rate of the currencies are basically the gauge fixing, and the gauges are basically, I mean, the difference between the gauges are basically dependent on that particular area of that currency.
Yeah, in that the physical quantity I defined is what amount of profit that person is making by doing a closed loop.
Okay.
And now what kind of gauge transformation I can do in this problem. So this is the kind of gauge transformation I do. So similarly here, actually this problem is the reason Maldacena chose this problem is because you can ask the same point, that what kind of phase you accumulate by doing a closed path. That is what we learned in Arnold Bohm, right? That is equivalent to how much magnetic field is there in the middle. This is why these two examples are very similar. And the fact that does it depend on how you measure your wave function locally, which means what part of that depends on the fact that you have an arbitrary phase factor to the wave function at every point in space-time. So this is the question of a gauge theory.
Can you repeat the last statement?
Yeah, so what is the magnetic field? How is the magnetic field affecting the wave function? It affects that if I put a magnetic field in a closed loop, if there is a magnetic field, then if the particle goes in a closed loop, it picks up a flux, right? That is what we learned. It picks up a phase, right? That is what we learned in
Yes.
the Then the question we want to ask, will that phase depend on the fact that if I do a local e to the power I alpha xt transformation to the wave function, will that phase depend on that transformation? If it doesn't, which it doesn't, we just saw that is the whole point of this, then we can say electromagnetic theory, quantum mechanics plus electrodynamics is a U1 gauge theory. Make sense?
Yeah.
Okay, so this is the point I'm trying to make throughout. Okay, these extra examples are just to make your build some intuition, but the if you just want to stick to the calculation, that's also fine. The calculation straightforwardly tells you that there is a U1 gauge invariance. There is of course a global gauge invariance, which is of course there, but then there is a local gauge invariance as well, and that demands the existence of electric field and magnetic field. So that is roughly everything I wanted to tell. And you can actually keep this discussion in mind when you study relativity, and especially special and general theory of relativity, because gravity is also a gauge theory, in the sense that if you do a you can so what do you demand in special theory of relativity? Physics is invariant in all inertial field. That's a special condition, because you are asking for invariance, the field invariance, and that gives you all this clock transformation, etc. And that also can be thought very in a simple manner. Of course it's simple now, but it was not simple when Einstein found it, because if you remember, we discussed this question that uh, when we are doing quantum mechanics 1, that what is time actually. So and we landed on the conclusion that time is actually motion. So there is no time unless there is motion. So that was the idea Einstein simply had. Einstein thought motion is relative, then why not time be relative as well? It's of course not an easy idea to have. It sounds easy now the way I'm telling you. So similarly, he asked the question that what if there are two systems which are accelerating with respect to each other? Then one of them, so then what is equivalent between them? The inertia mass. And, and that led to the equivalence principle. So it's also a kind of a gauge perspective, which says, what do you measure actually? What are you measuring? And what does it and does it depend on whether you actually have a gravity field, or the object is just accelerating with g acceleration, right? And then an extension of that is all flat. There is nothing local there yet. Now to bring locality into that, what he brought, he started with the idea that that your theory should be invariant to a how do you measure space and time. That means if you locally distort your space and locally distort your time to give a local transformation, then your theory should adjust to it with an additional field, which is gravity. So this viewpoint, you can learn this when you learn gravity more properly, and that leads to the gauge theory of gravity. But in this whole picture, you don't need quantum mechanics anywhere, and that is why it's so difficult to bring quantum mechanics and gravity in the same footing. Yeah, I will share everything in Piazza. Yeah. So this
Sir,
idea
can
I
you
just
please
want to, yeah.
explain a little bit about the time is if there is no motion, then there is no time.
Yeah, so can someone else
Uh,
explain? We discussed this extensively in last semester. Can someone else explain that instead of me? So imagine the following. Uh, can you have any measurement or perception of time if nothing is moving? How do you measure time, right? You measure time with respect to some standardized motion, like some clock state, or some motion of earth, or motion of a pendulum, something, right? So what is a measurement of time? Measurement of time is a relative motion. If you are kept in a closed if you are in a space where nothing is moving, can you have a perception of time? So think about that point, right?
okay.
How we measure time, it's from the perception of a two relative motion, right? Like a
But
clock is
that
moving,
is
you are
my
not.
measurement. Like
Yeah,
if
but yeah, so this is actually this is not so easy. This is the point. So we like to think that time is something absolute that is going on its own, right? Even if we are not measuring, but that is not true. I mean, it's how we are encouraged to think philosophically, because we know that time goes on anyways, you get old and you die and all that. But it's a biological, it's also a biological motion. Even if you're not measuring with your clock, your body is measuring it, right? So let's say you are asleep for 10 hours, and your brain didn't register that, right? Your brain doesn't feel any time passage, but your body got 10 hour older, right? It had the appropriate number of heartbeats, so somewhere the measurement happened, some motion happened somewhere, right? So the thought that time is absolute is it's very hard to throw away that thought. And that's why Einstein is Einstein. I mean, someone had that courage to think, and even before there were philosophers who thought that, but they didn't pursue it technically like the way Einstein did. But the idea is simply, you cannot have a notion of time, you cannot even define time, like you cannot even define distance unless you have another object, right? The space fleet, the spaceship example, right? If there is only one spaceship in the whole universe, then there is no concept of its position and distance or anything, right? So time is similar. So if there is only one system that is not moving against anything, then you cannot have a notion of time. So then the idea Einstein had was very simple. He said, if motion is relative, then why not the measurement of motion, that is time, is also relative? Then of course that it is not so easy just from that idea to land on the rest. But this idea is rooted on this simple logical argument, which takes a lot of courage to make. Okay, make sense?
Yes, sir.
Okay.
Sir, so to establish that global gauge invariant, we have to connect all the local gauge invariant with the same parameter.
What do you mean
There
by
must
that? Global is
means
simply the fact that if I multiply my phases and by an e to the power alpha, nothing nowhere changes. It's a trivial fact, right?
hmm,
Global alpha.
so if we connect two systems who have that local gauge invariance, so if we
Ah,
want to connect them,
hmm.
then the parameter which we are adding with them, they must be same
Yes.
to connect them in
Hmm.
between. Is
Hmm.
that right?
Yes.
So structurally, when we collect all the local gauge invariant systems,
Hmm.
then they all must be connected with the same parameter, which is
Yeah. So if you
one kind
want
of
your correct, if you want your whole theory to be um,
means
gauge
unified one
invariant,
unified theory.
correct,
Then
then you have to fix the gauge accordingly. But this statement is you should not stretch this conclusion from the spaceship example. The reason is the
hmm,
spaceship example is a trivial example because
hmm,
the objects you are coupling are same type, both are distance, right?
yes, yes, yes.
But when you are coupling matter field and gauge field, they are not same thing, they are different thing. It's an oversimplified cartoon picture. Okay,
Hmm, hmm, hmm,
then
hmm,
it's a bit tricky to think about that. And they are actually debated subject because you won't find it in textbook. I read this stuff in some paper and some discussion like that. So it's not so easy how to fix that when these are different type of objects are coupling. Okay, and this
hmm,
is an
hmm,
oversimplified example, of course. And usually you will see that the coupling term is the one which breaks. So then you might think, if what is the even the role of a gauge field, if it is an object that doesn't change something, is it a mere convenience or there is something more into it? So that point is you can argue that point by this coupling argument, but I don't want to get into that, because to discuss the coupling argument properly, you have to give this a and phi both a field status, which is not there in the quantum mechanics course, in quantum mechanics 2 at least. It will be there in quantum field theory. And the reason is, we earlier discussed that time cannot be an operator, right? Because if you make time an operator, then you have to incorporate negative energy, which cannot come in a single particle quantum mechanics. So that is why time, status of time is very different from status of position. And but you cannot promote time as a parameter in this framework, but you can demote position as a parameter from a operator to a you cannot make time a operator, but you can make position a not a operator, a parameter. So that is the key idea of field theory, where you take space and time both as parameter, and psi is a field on that of that parameter. So then you get a different view on this problem. But of course, this problem doesn't appear in many body physics, because in many body physics you can have in principle negative energy. How to have that, how to explain that we'll learn later in this course, when you learn second quantization and relativistic quantum mechanics. There you can in principle do that, but even that will cause some other kind of difficulties. So that is why generally that is one of the reasons why you treat all this as a field theory. Okay. Yeah, this is just a fun discussion. Don't worry if you don't fully understand it. Just appreciate the point that quantum mechanics is a gauge theory, and for that you need electrodynamics. The how to incorporate gravity in this picture and all are not very non-trivial and debated area of research. There are 2-3 different ways of doing it, and people don't agree with each other, etc.
Sir, one more question.
Yeah.
Can you just go to that part of presence of that solenoid in that interference experiment? Here, if we no, not this one, the next part where
Oh,
there
I
are
see.
two slits. Here, I am saying that if you said that if we tune the magnetic field in a some way, that the interference pattern can get
Yeah.
lost. Does it
Yeah.
imply or implicate that at that very moment the wave nature of the particle is lost, or
Yeah, but
the
here you are not doing any measurement. It's a what happens at the slit is measurement, but whatever you are doing, you are changing the magnetic field, etc. That is not a measurement. That is
so
like
it
a
is
transformation, but no measurement.
but it is killing the wave nature of the
You see, you are trying to
particle,
say,
right?
yeah, but it kills only if you tune it by appropriate amount, right? If you
Yes,
kill,
but at that very moment it is killing the nature of the wave.
yeah, so
So
it is causing interference. Interference has a phase thing, right? So you are messing with that
hmm.
phase, and that's why the interference, destructive interference, is getting modified. That is all
so
that is happening. But
so
you were
in
trying to
that
say,
sense,
can I interpret as a you were trying to
so
say at
I
that
am trying to
magical.
say that it just uh, destructive interference which is does not create any interference pattern, or it is anything
It can
that is
count as a
that
measurement, you are saying.
that becomes a deterministic kind of thing.
No,
Uh,
because even if you remember, when we discussed the Stern-Gerlach experiments, there is also a magnetic field. What does that
yes,
magnetic
yes.
field do?
Hmm.
It doesn't magnetic field doesn't cause a measurement. A measurement in this
When we
context
do the
means
measurement, it collapses to a state.
measurement means you
Mm-hmm.
know where the particle is.
Mm-hmm.
The only
Mm-hmm.
thing is here is where the particle is in this context. Of course, if you are doing a Stern-Gerlach, there you ask the question, what is the spin of the particle? That is measurement. So depending on your
Right.
setup, it
Mm-hmm.
decides what counts as measurement in that context. Okay.
Okay. Mm-hmm.
Okay. Everybody is more puzzled or less puzzled. Okay. Think
You
about this.
presented a lot of mind-bending things in one class.
Okay, yeah, that is the problem of Saturday classes. Every time I get a free time, that thing happens. Okay, okay. So think about this. Think about these ideas, and don't think physics as like okay, this is quantum, this is electrodynamics, this is gravity. It's not like that. Nature doesn't know all these boundaries. So it's all one set of principles which is appearing here and there. So think about, view it like that, and try to read all the subjects like that. Okay, I think it went on long, so I was supposed to finish at 3. Anyways, this happened a lot in last semester, last batch, and they complained a lot for that. Anyways, mm, that's all for today. So next day we start with time reversal, which is another very interesting idea, where you ask the question, if you think about this as a head start, that why do you want to even think about it, because it doesn't happen in nature, there is no going back in time funda, then why it appears, why it's such a big deal about time reversal. Think about it.
Yes, we know about time evolution, but it is
Yeah, why
reversal.
reversal? You are not going back in time anyways, then why make a fuss about it? So think about this point for Monday's
Well,
class.
I mean,
Uh,
I'm not sure if my question is making will make sense or not.
okay.
But I mean, the antiparticles we know, or I like the diagrams, Feynman diagrams or something to uh, say some to explain some particle interaction, say. So
Hmm.
we say that the antiparticles basically move backward in time and they complete the path, like the
Yeah. So
interaction of two electrons or so. So, like, if there is no time travel backwards, like we cannot go to the past, then why do we say that antiparticles go
okay, that is more
backward?
like a convenient picture to describe it, but nevertheless, you will see in the yeah. So let's postpone this question for when we come across. We will come across antiparticle at the last part of the class when you talk about Dirac equations, and it actually comes in handy because there are holes in many body physics. You have electron and hole, right? Holes are basically antiparticle of electron.
Yeah.
So we will discuss this question more precisely in that, but this statement is more like a convenience, that as a convenience in calculation, that they are symmetric partner. So you can say that it this something is moving forward, then the partner is the equation it satisfies, like
Sir, hole is antiparticle of electron.
yes.
Then what is positron? Hmm.
Positron, there is no positron in condensed matter. Condensed matter context, you have hole and
Okay,
electron,
okay,
and
okay,
positron when the ground state is a vacuum. It appears it's the same thing named differently in different field, high energy and condensed matter.
okay, okay,
Technically, operation is that here the ground state is a many body ground state. So hole is absence of electron, but in you will see in relativity, in relativistic quantum mechanics, in Dirac equation, you have to imagine that the ground state is not, the vacuum is not empty, and this is an hypothesis. There is not, and this hypothesis is sensible in condensed matter, but it's a peculiar hypothesis in high energy, or when you try to say that absolute vacuum is not vacuum. So that's where the concept of positron will emerge. Although the concept is peculiar,
okay.
but the object is real because the experimental evidence of positron. So we will come across this. Don't jump into this. Go step by step, and think about why we need time reversal at all. Such a peculiar concept. Like, think also that why we need gauge symmetry at all. I tried to explain you why you need gauge transformation, gauge symmetry. So similarly, try to get in a developer mindset rather than consumer mindset. Like, try to think from the perspective of the people who developed the subject. That why did they bring it in? Why did they think about it?
Sir, in that sense, that gauge invariance, that gauge theory is most fundamental. Means
Yes,
we can
you can
apply it
think. You can
anywhere,
think in that way.
anywhere.
Oh, yeah. So the definition of fundamental is a little tricky, but you can demand that starting by first of all, gauge theory is a very natural demand. It says certain things you have introduced for a description or your theory, and certain things are actually measurables. So the interrelation between them is, and this is there in any theory, right? So that is where the gauge theory is not just a matter of electrodynamics, it's everywhere, even economics. So that is the idea.
Okay, okay. Hmm. Will you be sharing this in
Yeah, I will
mail?
share everything.
Okay,
I will
okay,
share
okay,
everything,
okay, sir.
all these lectures and notes, wherever it is there. Yeah. Okay, see you then. Yeah, I will. A previous one was I have to see how to edit it because it's a long lecture of nothing. Only 15 minutes was actual lecture, and I will share it all those things by today. Okay, see you then.